Okay, in this screencast we're going to talk about liquid vapor equilibrium. Spell equilibrium, right? There we go. Alright, and really if we just start off with a sketch of the vapor pressure of a liquid versus temperature, the graph would look like this. If you recall, at 1 atmosphere, which is atmospheric pressure, okay, the temperature would be the boiling point, okay, at 1 atmosphere. Alright, and let's just quick define boiling point. Boiling point is the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. Okay. The other thing to just quickly remember is graphs that look like this, and I'm not drawing this to scale. This is energy and this is temperature, and remember that you've got your melting point and your boiling point, melting point, and it's these points where you are breaking up the intermolecular forces and changing phase. So the energy is going into changing phase, and this is related to that boiling point and that vapor pressure equilibrium. Alright, so let's take another closer look at this vapor pressure versus temperature. If we look at this part of the scale right here, okay, at this part few particles have enough kinetic energy to leave the liquid phase. Okay. And if we look at this end of the curve, okay, obviously if the other end is few particles, this is more particles have enough kinetic energy to leave the liquid phase. And this is all goes back to that Maxwell-Boltzmann curve with the number of particles and the kinetic energy. Okay, and remember, at a higher temperature the curve just gets flattened out. So at the particular kinetic energy needed to leave the liquid phase, you can hopefully see at the higher temperature there would be more particles with enough energy to do so. All right, and this is all breaking those intermolecular forces. Okay, if I have that sample of water and an open system, those particles with enough kinetic energy leave the system, okay, and evaporate. So the particles with the higher kinetic energy leave the system. This leaves behind particles with lower energy, and that essentially decreases the temperature of the liquid left. Okay. Okay, if this system is closed, what ends up happening is I have particles leaving, particles moving back, and I end up with a dynamic equilibrium. The vapor pressure up here is only temperature dependent. That says temperature dependent. Okay. One last thing to leave with in this liquid to vapor equilibrium. During boiling, and I just want to write it down. I'd said it previously. During boiling, the IMFs completely broken. Completely broken. Remember that these are the intermolecular forces, not covalent bonds. Not covalent bonds, just the intermolecular forces. Okay. Remember, for an ideal gas, there are no attractive forces between particles. Okay, and keeping all this in mind, the stronger intermolecular forces, the higher the boiling point, because you need more energy to break those intermolecular forces. Remember, intermolecular forces consist of London dispersion forces. Those are the polarizability of the electron cloud present in all covalent particles. There's dipole, polar molecules, and then there's H bonding, which is present between molecules when hydrogen is directly bonded to a fluorine, oxygen, or nitrogen. Those highly electronegative atoms pulling the electron from the hydrogen, leaving hydrogen with a full +1 charge. Very attractive. That ends the screencast.